All right, this is the first example of chapter 9. It is question 195. Let's read the question. Question 195. Three wires sitting at the corner of a square, all carrying a current of 2 ampere into the page. Calculate the magnitude of the magnetic field at point P if the length of each side of the square is 1 centimeter. All right, so let's have a look at the diagram. We have three wires, the first one, second one, and third one, that are carrying a current of I1, I2, and I3. Now we are told that all the current are the same. They are 2 ampere each. We are also told that the wire is sitting at the corner of a square, and the square has side of 1 centimeter or 0.01 meter. All right, so here, this is a classic case of we need to calculate the magnetic field at from multiple current carrying wire, and we need to use the principle of superposition to add them up. So let's have a look, let's say, at the first wire over here, I1. So we want to find in which direction the magnetic field is pointing first. We use a right hand rule. We take our thumb, point it into the board because the current is going to the board, and the curl of our finger tell us in which direction the current is moving. In this case, it is clockwise. So the current is moving, the magnetic field is moving in that direction. So what that means is, remember, if we were to draw a straight line from the center of the wire to where we're considering the magnetic field, there will be an angle of 90 degrees between them. And since it's going clockwise, well, it's pointing in the clockwise direction. So from the point of view of the first wire, the magnetic field will be moving in that direction, which means that at point P, the magnetic field of the first wire, B1, will be pointing downward. All right, we follow a similar logic for the two other wires. And note, their current are pointing in the same direction, which means that we will follow a similar logic. If we look at I2, the magnetic field will be pointing with an angle. Now, this case is fairly straightforward. It's a square, which means that the angle will be 45 degrees. We will see some other example where it might not be as obvious, all right? We then look at the third wire, follow the same logic. In this case, what we see is the magnetic field is pointing to the left. Now, what we need to do, we know the direction now, we need to add the vector up, we need to find the magnitude also. So we're going to use the Biot-Savart law to find the magnitude. So remember, the magnitude of the vector B, the magnetic field, is dependent on the permeability of free space multiplied by the current, divided by 2 pi multiplied by the distance between the current carrying wire and the point we are considering. So in vector form, the net magnetic field is equal to B1 plus B2 plus B3. All right, the first step we're going to do is we are going to be drawing on a vector diagram the direction of each of these three vectors. So we have a vector diagram, x and y axis again. The first one, B1, is pointing downward, so in the negative y direction. B2 is pointing with an angle to the left of the negative y-axis. And we know because it's a square that if you look at the magnetic field here, it's going 1 centimeter down, 1 centimeter to the right. Well, a triangle with two sides having exactly the same length is a triangle with two sides of 45 degrees. Obviously a right triangle. If there's no right angle, this might be different. But in all the cases we're considering, it's always a right triangle we're considering. All right, so 45 degree, B3 is pointing to the left. All right, we got the rough idea of the direction. Now we need to calculate the magnitude of each vector using the Biot-Savart law. Now note, the principle here will be the same for all the vector. The only thing, all the current carrying wire, the only difference will be distance from the wire to the point P. So if we consider the first wire, it is at the distance of 0.01 meter. So we got permeability of free space multiplied by the current is 2. Note that the 2 and the 2 will cancel out. We have pi over here, and we got 0.01 over here. Which give us 4 multiplied by 10 to the power minus 5 Tesla. So I did not write the unit, I'm kind of running out of space, but it is still in Tesla. We follow the same logic for the second wire. However, this one is not at 1 centimeter. It is at 1 centimeter square plus 1 centimeter square root of that answer. We use the Pythagorean theorem, and if we draw a right triangle with this side as a right angle, well, this will be the hypotenuse, the distance between I2 and P. All right, so the distance become 1.4 centimeter or 0.0141 meter. We input all these values, give us a slightly lower magnetic field of 2.83 multiplied by 10 power minus 5, again in Tesla. All right, same logic with B3. Well, note, B3 has the same current and same distance as B1, so it is exactly the same magnitude. Note, they share the same magnitude. It does not mean that they are the same vector. Their direction is very different. B3 is pointing in the negative x, B1 is pointing in the negative y. That's an important distinction. All right, so at this point, we got the magnitude, we need the angle, we need the magnitude also, so the top part is not needed. Pause the video now if you need to write down anything. I'm gonna erase the top part. All right, as is always the case, with 2D vector, we need to break them down into their 1D component, and we are now expert in doing that, so I'm gonna do it in one line. So Bx, and by the way, when I say Bx without a number, it just means the net magnetic field. It's easier to write it that way, it's less cumbersome. So Bx is equal to all the vector or the component of the vector pointing in the x direction. So the first one pointing in the x is B3. So we have minus B3, and note there's no arrow, so we're talking minus the magnitude. So we have another vector B2. Now note B2 is pointing in the negative y and the negative x at the same time. If we want the x component, it is opposite to this angle, we will need to use the sign. So minus B2 sine of the angle 45 degree in this case. All right, and I'm gonna add it minus 0, minus or plus or minus 0, does not matter. Just to state that B1 basically has no component in the x. All right, let's repeat the same step, but in the y direction now. All right, so in the y direction, we got minus B1 pointing down, and we got minus B2 cosine of 45 degree in this case. And plus minus 0, let's say, just to highlight again that B3 is strictly a 1D vector in the x direction. All right, so let's compute the value of in the x direction. Okay, so that's convenient. So we get minus 6 multiplied by 10 power minus 5 Tesla in the x direction, and cosine and sine, these will be identical. So we got minus 6 multiplied by 10 power minus 5 Tesla in the y direction. So the resultant vector will be a vector in the pointing diagonally to the bottom left part. All right. So let's recreate the complete vector. We want to check the hypotenuse, or the magnitude actually, of the net vector. So it's, we get the magnitude is 8.48, sorry, multiplied by 10 minus 5 Tesla. And if we're looking for the angle, well, this one will be very straightforward. We have to draw both vector are identical, they share the same length, so we don't even need to do any calculation. It will be a 45 degree vector, so 45 degree vector to the left of the negative y-axis. So B is equal to 8.48 multiplied by 10 power minus 5, 45 degree to the left of y negative. All right, so that's a big question. Note in the slide there are some smaller questions just before that one. Honestly, they are more like warm-up question. You can give it a try, but all the concepts are shown in that question together, and we are going to be tackling question 198 after that. And with these two questions, really they are longer questions, but we got a bit of everything in there. All right, but if you feel that you need some practice, there are some easier examples just as a warm-up before this question. This one, take many concepts together all at once. All right, so we are done with this question. Let's move on to another one.